Hey everyone, and welcome to this explainer. Today, we're taking a journey inside the atom, literally decoding the architecture of the universe. We'll be climbing the cognitive ladder, starting right from ancient philosophy and going all the way to modern quantum applications. It's time to look closely at the very building blocks of matter and see exactly how our understanding has evolved over thousands of years. Let's get into it.
Here's our roadmap for the journey today. First, remembering the atomic pioneers. Second, understanding the atomic structure. Then, applying the Bohr rules, analyzing atomic identity, evaluating isotopes and isobars, and finally, creating the nuclear future.
All right, let's kick things off with Section 1, Remembering the Atomic Pioneers.
It's fascinating, isn't it? The philosophical idea of the indivisible paramanu was brilliantly proposed by Acharya Kannada in ancient India, long before modern tech. This concept gradually evolved through rigorous scientific experiments. By 1808, John Dalton gave us the first formal scientific theory of an indivisible atom. But, as we know, late 19th century radioactivity threw a massive spanner in the works. In 1897, J.J. Thomson's cathode ray experiments proved atoms actually contain negatively charged particles, electrons, which gave us the famous plum pudding model. Then, in 1911, Rutherford's legendary gold foil experiment completely shattered that idea, revealing a tiny, densely packed positive nucleus. And finally, in 1913, Niels Bohr introduced his model of stationary, stable energy shells to explain exactly why these atoms don't just collapse in on themselves.
Moving right along to Section 2, Understanding the Atomic Structure.
So, this perfectly illustrates the delicate balance we find within the atom. We're looking at three main subatomic particles. You've got electrons orbiting outside the nucleus. They carry a -1 charge, and honestly, their mass is so incredibly tiny we just consider it negligible. Then you've got the heavy lifters packed safely inside that dense nucleus. There are protons, discovered by Rutherford, carrying a +1 charge, and neutrons, which James Chadwick found later carrying 0 charge. Both of these have a mass of roughly 1 atomic mass unit. The absolute vital takeaway here, the electrical neutrality of the atom. It perfectly balances the negative electrons outside with the positive protons on the inside.
Now, take a second to wrap your head around the sheer scale we're talking about here. When Rutherford fired those alpha particles at that incredibly thin gold foil, the vast majority just passed completely straight through. This actually proved that an atom's diameter is roughly 10 to the power of 5 times larger than its nucleus. To put that into perspective, if the atom were the size of an entire cricket ground, the dense nucleus, which by the way holds almost all of the mass, would merely be a single grain of sand resting exactly at the center. So yeah, an atom is overwhelmingly just empty space. Wild, right?
Okay, let's jump to Section 3, Applying the Bohr rules.
Now that we know the parts, we need to know how they behave. The crucial point here is following these 3 steps to determine an element's electronic configuration because that completely dictates its chemical behavior and valency. Step 1. We use the 2n² rule. This handy formula tells us the maximum capacity for the K, L, M, and N shells. Step 2, and this is absolutely critical. Regardless of total capacity, the outermost valence shell is limited to a maximum of 8 electrons. Why? To achieve a stable octet, just like those highly unreactive noble gases. And step 3, electrons don't just jump around randomly. They have to fill these shells stepwise, starting strictly from the inner K shell and systematically moving outward.
Let's transition to Section 4, Analyzing Atomic Identity.
How do we actually tell these elements apart? Well, the atomic number, represented by the capital letter Z, is literally the absolute fingerprint of an element. It's simply the total number of protons located right there in an atom's nucleus. Every single element on the periodic table has a completely unique atomic number. And remember what we said about electrical neutrality? Because atoms strive for that balance, in a neutral atom, this Z value perfectly equals the number of orbiting electrons too.
Meanwhile, we have the mass number, represented by the capital letter A. This accounts for all the heavy lifting occurring in the dense center of the atom. It represents the total number of nucleons, meaning just the protons plus the neutrons combined. When we write this out using standard atomic notation, you'll see the mass number sitting at the upper left of the chemical symbol and the atomic number down at the lower left.
All right, let's put this into practice and test those higher-order thinking skills. If a carbon atom has a mass number, or A, of 12 and an atomic number, or Z, of 6, how many neutrons are we looking at? Well, since the mass number is just protons plus neutrons, if we simply subtract Z from A, we can clearly deduce that there are exactly 6 neutrons. It really is an elegant and entirely logical system once you get the hang of it.
Moving into Section 5, Evaluating Isotopes and Isobars.
You've got to notice the stark contrast between these two concepts because they are super easy to confuse. On the left, we have isotopes. These are atoms of the exact same element. Think carbon-12, 13, and 14. They share the same atomic number, Z. That means they have identical electron configurations and, naturally, very similar chemical properties. However, their mass numbers are different simply because they contain a different number of neutrons. Now, on the right, we have isobars. These are entirely different elements altogether, like argon-40 and calcium-40. They have completely different atomic numbers, but they just happen to share the exact same mass number. Same mass, totally different identity.
And finally, Section 6, Creating the Nuclear Future.
Grounded deeply in Indian knowledge systems, Homi Jahangir Baba's visionary leadership took all this theoretical physics and transformed it into a tangible, world-changing reality. He established premier institutions like the Baba Atomic Research Center, or BARC. His work drove forward a massive, peaceful nuclear energy program designed to generate clean electricity, advance agricultural research, and completely revolutionize modern medicine. Speaking of medicine, the exact isotopic variations we just evaluated are now vital, life-saving tools that doctors use every single day. For instance, cobalt-60 is famously utilized for highly targeted cancer treatment. Iodine-131 is an essential tool for treating goiter and thyroid issues. We also use uranium-235 as incredibly potent nuclear fuel, and carbon-14 allows historians and scientists to accurately date ancient fossils and artifacts. So understanding the atom isn't just some abstract theory, it is highly practical science that literally shapes our modern world.
As modern quantum theory moves far beyond Bohr's fixed circular paths and dives straight into dynamic, highly complex electron probability clouds, it really leaves us wondering. From ancient Paramenus to today's cutting-edge quantum physics, what unseen mysteries still remain hidden deep inside the atom? What new particles will we discover next to fuel humanity's next great technological leap?
The journey of discovery is far from over. To truly master these complex electronic configurations and tackle those tricky average atomic mass calculations yourself, you've got to visit eatanudge.in today. You can rigorously test your chemistry reasoning with their exceptional CBSE-aligned question banks. Dive into highly engaging HOTS competency-based scenarios and use their unique 5-step nudge system, which is specifically designed to build genuine mastery. Thanks for joining me on this explainer. To explore the architecture of the universe, I'll catch you in the next one.